start a new recording. Okay, so the main topic of this week are algorithms and data structures. It's 2 presentations. I try to limit the number of slides so we don't run out of time this week. So at the end of this presentation, you should have learned what the difference is between a linear, quadratic, and exponential runtime of an algorithm. So we call that the time complexity, and you can think about it as a super fast plane. In algorithms terms, you can call that a linear algorithm, or maybe a slow van, and that would be quadratic time complexity, or exponential time complexity, which is like a snail or something. And we will also see 2 algorithms for sorting, selection sort and quicksort. I also talk a little bit more about why sorting is so important in this presentation. So the main motivation is that even if today's computers are very powerful, you can do billions of computations every second. There's also the problem is that what we want to compute, the types of things we compute, are also becoming more and more complex. So designing efficient algorithms is really important, and especially in data engineering, because in data engineering, you typically work with big input data sets, so millions, billions of tuples. And if you then have an inefficient algorithm, it can quickly lead to programs that never finish, or maybe finish in a couple of hours or weeks. But often with a more efficient algorithm, you can really go from hours to minutes, or from minutes to seconds, or from seconds to milliseconds. So that's also important financially, because in the cloud, if you rent different servers, that obviously costs money. So in this lecture, we will try to build an intuition of the complexity of algorithms. So complexity is another word for runtime. So we can make also an estimate of what resources we need. And then there is a small cartoon. Well, you can have a look at it after the presentation. So what are algorithms and data structures? So first, this is the reference book we will be using, Introduction to Algorithms by Cormen and other authors. So it's basically like a cookbook. So every program runs algorithms, uses data structures, and you can consider this book as a cookbook, and all the different algorithms and data structures as recipes. So there are many out there. The book is also more than 1,000 pages, so I don't expect you to know all of these algorithms, but just give an intuition of some of the more basic algorithms, and not basic, but the more essential algorithms, because that's really important in general, as these are really the building blocks of computer science, and of any application depends on these concepts. And so the book consists of 7 parts. We will cover the introduction. So that's chapter 2, getting started. Chapter 2, the second part in the book is on sorting algorithms. The third part is on data structures, and there we will cover chapter 10, which is on elementary data structures, chapter 11, which is on hash tables, and chapter 12, which is on binary search trees. And then the last 3 parts of the book we won't discuss, but just to give an idea, is that part 4 and 5 consist of more advanced algorithms and data structures. Part 6 contains graph algorithms, and part 7 various different topics. So the definition of an algorithm. So an algorithm consists of a finite set, a small number of instructions, and together this set of instructions solves a well-defined problem in a finite number of steps. So obviously, if your computer is going to take forever, then it's not. If your program or your algorithm is going to run forever, that's not useful. So every problem has its specific solution and is designed for a specific input data, but you have to make sure that it covers all possible instances of that input data. So an algorithm should always work for each type of input you give to it. And to solve a problem, there are typically some restrictions. So the algorithm can only use a limited amount of memory, and it also should finish in a reasonable amount of time. So an algorithm has a lot of similarity with a mathematical function in the sense that it has an input argument and has an output. So for example, a sorting algorithm takes as input a list or an array of numbers, and it can also be strings or something else. And then we apply our set of instructions. And finally, as an output, we return a sorted list of numbers. And we do that in a finite amount of time. So that's an example for a sorting algorithm. So there are different types of problems, and each specific problem is solved by a different algorithm. And often, for one task, there are several variations, so several algorithms that solve the same problem, but one of those solutions or one of those algorithms is more efficient than the other one. And that's what we're going to look into today. Finally, algorithms need to do some bookkeeping of the data. So the algorithms have a number of variables, and you want to do some kind of bookkeeping. And the performance of this bookkeeping depends on the chosen data structures. So each algorithm depends on certain data structures, and so those are also very essential. Okay, algorithms and their runtime. So we're now going to introduce runtime and the way we typically measure it in computer science. So the computational complexity of an algorithm. So what is it? Well, the complexity analysis of an algorithm determines how much the execution time, or sometimes also the memory, increases with an increase in input data. So we're mainly interested in how much does an algorithm scale. So if you have a small list consisting of 5 elements, it doesn't really matter which algorithm you use, because every algorithm will finish in a couple of milliseconds. But if you want to sort 1 million numbers or billions of numbers, then we typically look at the complexity. So we look at how much time does the algorithm takes in function of the size of the input data. So that's complexity. So it allows you to estimate the total execution time, the total amount of memory you need. It's based on the number of base operations. So your algorithm consists of a number of instructions or base operations, and you have to execute them one by one. And obviously the size of the input data. So if you're going to sort 1 million numbers, it will take a lot of more operations than just 10 numbers. So base operation is an operation that does not depend on the values of its inputs. So just think of the sum of 2 numbers is a base operation, reference a variable is a base operation. But if you want to take the sum of n elements in an array, okay, you're going to do n times that sum. So the sum of an array is not a base instruction. And also for sorting, if you want to sort 1,000 elements or sum 1,000 elements, that will take longer than 100 elements, so that's not a base operation. So here is the first small algorithm we show. We want to search for the largest number in a list or in an array. So here we have a list with all these numbers, and we want to find the maximum number. So if you go through the list, you see that the maximum number is 50. And so how do we compute that? Well, we loop over the array. So we say for e in range 0 to the length of the lists. So here I think there are 14 elements. So we go from 0 to 14. And then we compare the elements at index e. So that's lists and then the rectangular brackets e. If it's bigger than max. And we initialize max with minus infinity. So every number will be bigger than max. In this loop, the first number, so at index 0, will be bigger than max. So 20 will be bigger than max, and that becomes a new maximum. And then we increase e, so e becomes 1 in our for loop. We check list 1. If it's bigger than max, max is currently 20. At index 1, the list has value 30. So 30 is bigger than 20, and 30 becomes a new max. And we continue, and finally we find that 50 is the max overall. Simple algorithm. What does it do? It checks all the elements in the array, and the base operation it does every loop is it does a comparison of the current max value with the element at index e, and we assume that takes a constant amount of time. And so it takes a constant amount of time to increase e by 1, to reference list e and compare list e with max. But we have to execute this base operation n times. So for each element in the list, we're going to compare the eth value with the current maximum. So we say the complexity, which is the runtime actually, not complexity, which is denoted here by the function t, given a list of n elements, is equal to a constant factor times n. So I think that's a good way to mathematically define the runtime of this algorithm for finding the maximum numbers in an unsorted list. So the initialization of max is also an operation. So actually, you're right. So actually, we would have to say that function t is the constant factor c times n plus another constant factor. But actually, I ignored it in this case. But to be perfectly correct, you're absolutely right. Of course, it doesn't matter that much because it's only initialized once, but we will see that further on. So given that this function t is linear, we say the execution time increases linearly with the size of the inputs. So linear program is often very nice. So that means if you want to process 1,000, if you can find the maximum in a list of 1,000 elements and it takes 1 second, then if you have a list of 1,000,000 elements, it takes 1,000 seconds. So a linear program is okay. But we will see later on that we can do this much more efficiently. Later, and I mean here on these slides. So assume our input now is a sorted list. So we have the same list as before, but we sort it. We ignore at this time the costs or the runtime of sorting the list in itself. But if we have a sorted list, we can just compute the maximum as the last element in the list. So this is a trivial example of an algorithm. And here you have to check 0 elements in the array. And we only have to reference the last element in the array, so we can assume it's a constant amount of time. And here we say the function t for any list of input size n is just equal to a constant value. So even if you have billions of elements, if they are stored or supplied in a sorted list, then you can just take the last element and it will always take a constant amount of time. So that's another example. So this is an example of a program with a quadratic execution time. So here we have sum n. And what does it do? Well, it takes the sum of all numbers between 1 and n. So we have first our result, which is 0, and then we loop from 1 to n with index e. Then we loop again within each loop from 1 to n, and then we add the results of e plus y, and we accumulate those terms in one big result. And I've added a print statement here. And so if you look below, if you take the sum with n is 1, it's just 1 plus 1. If you take the sum with as parameter 2, we already have 4 terms, because we're going to loop from 1 to 2, and then again loop also from 1 to 2. So we have 1 plus 1, 1 plus 2, then 2 plus 1, 2 plus 2. So it quadruples, the number of terms quadruples with each increase in n. And so for sum 3, we have 9 terms. For sum 4, we have 16 terms. And you can see that this type of computation, if you type sum 1000, that will take some time. So this is an algorithm. It's just a synthetic example, but this is an algorithm, and you can imagine that for really large inputs, so for n equals 1,000,000, this will not finish in a couple of minutes. This will take hours to compute. So we say the execution time, t, is a constant factor times n squared. So depending on your argument here, n, it will take the number of instructions, and consequently the execution time will be squared to that input size. And then another example is matrix multiplication. So if you have a matrix and you want to multiply them, you multiply each row with each column, and then you take the sum of the pairwise elements and add them and store them for each position in the new matrix. So that means first you have to loop for e in the range 0 to n. So we assume there are n rows. Then you loop for y, which is the column index, and you loop from 0 to n again. So that's multiplied, so that's n times n loops you are doing. And then you still have to, so then you have every row, every column, and then you still have to take the dot product of each value in each row with each value in each column. So you again have a loop. So this is a cubic complexity. So the function t is a constant factor needed to do the addition here and reference the two values in each matrix and add them together in the output matrix. So that's a constant factor times n to the third power. So for matrices, you can say if you have really matrices consisting of billions of elements, which you sometimes have in machine learning, it will take quite some time to finish it. So let's go to the asymptotic analysis. So asymptotic, that means going from n to extreme values for n. So n is 1,000,000 or 1,000,000,000 times. So we're really looking at how does it scale with very large input data sets. And so for asymptotic analysis, it's usually not necessary to be exact. So we don't care about how many instructions are executed exactly. We just want to have an idea of how the execution time increases roughly with increase of the size in the input data. And so the order of magnitude is important. Obviously, when you have a small input, not obviously, but on a side note, when your input data is very small or two algorithms have the same order of complexity, the constant factors are important. So you have two algorithms, and one algorithm takes only half of the steps. Okay, that's a constant factor, but it's still important. But what's more important is that you have an algorithm. One is linear, one is quadratic. Yeah, there the difference will be much more important. So we're really looking at the order of magnitude. So that also mean, constant factors don't really much. If you're initializing, like in our maximum function, the initialization, it's not important. If we run 3 or 6 instructions every loop, that's also not important. So constant factors we ignore in the asymptotic analysis. Also, when you have different terms, like here we have the t function with the complexity of 10 times n to the third power plus n to the second power plus 40 times n plus 80. So 80, 40, and 10 we ignore. Those are constant factors. But we also ignore n to the power 2 and n and just n. Because if n is thousands, you will have 10 billions of steps required. But only 1 million of those are due to the quadratic term and the linear term of n. And so we're really only interested in the leading term. And so we make our function t a little bit more simpler. And then another thing with complexity is that you also always have a best, worst, and average execution time. For example, here's a small algorithm for finding an element in the list as search. So what you want to do is what does this do? We loop over all elements in the list. We check if the element at index e is equal to x. Actually, I made a small mistake here. The first input argument should be x, not L. And if we find it, we return true, and otherwise we return false. So search continues true if the number is contained in a list, and otherwise it returns false. So if you have this list here of sorted ordered numbers in this case, and we search for 1, well, in the best case, that's actually the best case, 1 is at the first index. So we're not going to do n loops. We just find 1 at the first index, return true. So actually, in the best case, this algorithm only requires 1 step. Even if you have millions of elements, if the element you want to search is the first one in the list, then in the best case, you only require 1 step. Now, the worst case is when the element is 9 or if the element is not in the list. Because if the element is not in the list, you still have to compare for each element of the list if it's equal to L. So in the worst case, you will have 9 steps in this example or n steps. So that's important because that means that sometimes your program is going to take a long time. It's going to take linear. So if you have billions if your list consists of billions of items, in the worst case, you have to really go over each element in your list. And then you have the average case. So in average, if you would just search in this list a random number between 1 and 9, on average, it would take n divided by 2 steps. So if you would run search on any input number between 1 and 9 and repeat it millions of times, on average, you will do 4.5 steps. So these are the 3 cases, best case, worst case, and average case. And we also take this into account when we do a complexity analysis. So we say, in the best case, this algorithm performs in constant time. In the worst case, it takes n steps, and in the average case, it takes n divided by 2 steps. So we make a distinction here. And the notation we use is the big O notation. So the big O notation is like a summary. It's like a label for each algorithm. If your algorithm has O(n), then it's a linear algorithm. If it has O(n squared), it's a quadratic algorithm. So we classify our algorithms based on this notation. So the first notation, so O, I forgot the name of the Greek letter, delta or something, no, I'm not sure. O with a little thing inside is used to denote the average time complexity. So in our previous example, the average complexity was n divided by 2. And there's a little formula here. Concerning a definition. So if you have a function t, in practice, it means you ignore all constant terms, only take the leading terms into account, and then you have the average runtime. But here in the definition, you actually see that it's an asymptotic analysis. So it means the average execution time should only hold when the size of the input is bigger than some n0. So that means that for small lists, the runtime can vary a little bit more. But starting from a big enough input, theta, yeah, sorry, theta, starting from a big enough input, we will see that the average time complexity is both an upper and a lower bound for the actual time function. And then the other notation we use is the big O notation, which denotes the upper bound of the execution time. So that's the worst case scenario. And so if we say it's O(n), that means in the worst case it takes n steps. And you can have your t function and multiply the upper bound by any constant, and it will always be higher. And so that's shown here in the graph next to it. And then finally, you have the omega notation, I guess. It's used to denote the lower bounds. So that's the best, in the best case. So that's a lower bound of the actual execution time. Now, usually the lower bound we're slightly less interested in, because that's the best case. And the best case, okay, it's nice if your algorithm runs super fast once in a while, but usually we're more concerned with the worst case. What's on what types of inputs what will the runtime be on the worst type of instances. So here the best case is just one step, but okay, that's not that interesting. That's by accident. For some types of inputs, it only takes one step. I think the average and the worst case are more important in practice. So here's an example. So we have a function t. It's a constant times n divided by 2, like our search problem. And the average execution time is there, a constant times n divided by 2. So here we can deduce that the execution time is linear, and both the average and the worst case time complexity are given here by O(n) and theta n. So we ignore constant factors. So the c also dividing by 2, it's also a constant factor, so we ignore it. So we just say the complexity is O(n), and the average time complexity is also theta n. And in the other case, we have a constant. The function t is given by a constant c1 times n squared plus a constant time n. So here again, we deduce the execution time is quadratic, and both the average and the worst case time complexity is given by big O(n) squared or theta n squared. So we again ignore constant factors and the lower order term. So we've talked about runtime until now, but the same can be said for memory. So for memory, you can analyze these kinds of t functions in a similar fashion. Usually you apply them to data structures. So each algorithm uses some type of data structure, and you apply the analysis to these data structures. So an example, if you want to create an array of n integers, you require n elements in memory. And if you have an n a matrix, a square matrix of n on n, you require n squared registers in memory. So that's a similar rationale. And often in algorithms, there's a time-space trade-off. So often you can improve the speed of your algorithm by using more memory, or your algorithms may become slightly slower if you lose less memory. So often there's a trade-off between memory and time when you're designing an algorithm. So here is an overview of the most common functions for representing execution time, and it's a colored graph here, and you see that constant algorithms, so for example, if all items are sorted in a list, and you want to compute the maximum, you can just take the last element, so that's constant time, that does not depend on the size of the input lists. Obviously, that's the best case, that has an excellent score here in big O complexity charts. And logarithmic programs, so that means logarithmic. For instance, if you have 1,000 numbers and you take log 10, that only if your n is 1,000 and you take log 10, that's only 10 steps you need to process an input list that has 1,000 elements. Or if it has 1,000,000 elements, log 10 of 1,000,000 is 1,000. So logarithmic, it's slightly worse than constant, but it's still a very flat line. It's only your input can be extremely large, and it will only take a couple of hundreds of thousands of instructions to compute your algorithm. Then you have linear, which is still fair. So you have to loop over each element in your data, but that's still quite fast. Log linear, which is here, has a bad rating in the complexity chart. I wouldn't classify it as bad. It's still manageable, but maybe with a log linear algorithm and extremely big input sizes, maybe it will impede real-time applications. If you have an algorithm that wants to compute something in real time, log linear is difficult for very large values of n. And then you have quadratic, and even worse, exponential. So there are a lot of known problems in computer science who are by nature exponential. So that means n is actually it's 2 to the power n. So n is in the exponents, or you can also take the factorial. So some types of problems are exponential, and there you really run into problems, because even for really small values of n, like n is 100, an exponential algorithm can take weeks to compute. So that's a little bit an overview of the different complexity classes there are. So let's say in the green, those are the airplanes. In the yellow and orange, those are the usual cars. And n square and especially exponentials, those are like snails, if you compare runtime. And then let's have a look at two sorting algorithms. So yeah, for algorithms and data structures, there are a lot of reference books. This is one from Knut, The Art of Computer Program, and it consists of several volumes. I'm not sure how many there are here. There are the 3 main ones, but I think there are more. Those are really thick books, quite complicated. And there's a quote from Bill Gates: if you're a really good programmer, read The Art of Computer Programming, and send me your resume if you can read the whole thing. Because these algorithms, yeah, they're hard to understand. Every algorithm that you have to learn, it some time to really understand it, and sometimes it also helps with a piece of paper and a pen to go over each step and pretend you're a computer to really grasp how an algorithm works. So algorithms, they're not easy to understand, and that's why Bill Gates is interested in you if you know a lot of them. So why sorting? Why focus on sorting algorithms? So often in many problems, especially in information retrieval, if you want to search like in Google, or in general, if you're storing data in databases, a lot of times your problem is going to take a much longer time if the input list is unordered. So often sorting is a first step in any application or the more complex algorithms. And sorting is also an interesting example of how a naive implementation can be less efficient than a carefully designed algorithm. So the carefully designed algorithm might be a little bit more complex, a little bit more code, but still, if the runtime decreases from n squared to n times log n, that's really important, and that makes a difference between taking hours or minutes. So two sorting algorithms, selection sort and quicksort. So the first one, selection sort. How does it work? I'm going to show the visualization. It's nicer to explain it. So here you have a set of numbers, 21, 65, 50, sorry, 11, 41, 47, 33. So these are not ordered. And we want to have a sorted output. So that's the last line. So you have 1, 11, and so on until the highest number. So how can you get from the first line to the last line? Well, first, and that's the first iteration, you compute the maximum. So the maximum, it's 65, 56, sorry, did a bit dyslexia going on. That's the highest number. So you loop over all elements in your list or your array, and you compute the maximum number, and you put that as the last number in your array. So you swap 56 with 33. And then we go to the second iteration. So that's the third line in the table. And we have 47, which is already on the second last position. And it's also the maximum, so actually we don't change anything. And then the next iteration, we again find the maximum number, but every time we find the maximum number in the first, before it was the first 7 elements, now 6, and now 5. At 41 is the maximum, so we don't change anything. Then we find 33, and we swap 33 with 11. So 33 is the new maximum, it's put last. Then we put 20 last, we put 11 last, and so on. And finally, our list is sorted. So that's selection sort. So we find the largest element in the list. That requires n comparisons for a list with n elements. We swap the last element in the list with the largest element. So swapping means just changing in the array, swapping the values between those two indexes. Then that's the first iteration. In the second iteration, we again find the largest element, actually the second largest element in the list, but we ignore the last element because that was already the maximum in the previous iteration. And we swap that second large element with the last but one, and we continue in that way. So that's selection sort. Here is the source code. So you see the swap operation. The swap operation in a list, it gets 2 indexes. So what it does, it takes the elements in the first index, then you override, that's the second line, list index 1 equals list index 2. So you override on that index on index 1, you put the value of the list at index 2, and then you do the reverse. So at index 2, you store your element, and you have to be careful to hold these elements in a temporary variable, because otherwise you cannot override in the list at the second index. So that's swapping, just changing two values in an array, and then the selection sort, it goes for E from 0 to the length of the lists. Then you find the maximum value as the code we saw before. So you just find the maximum value. You also keep the index at which the maximum element occurs in memory. So those are these lines. And then finally, you swap the maximum value and you put it at the end of the list. And in the first iteration, the end of the list is the length of the list minus E, which is 0, minus 1. So since arrays are indexed from 0, you don't have len list, but len list min 1 as the last index, and you do minus E. So the first time, if you have 7 elements, the last element, if you have a list of 7 elements, the length will be 7. So the last index will be 6. The second time it will be 5, 4, 3, 2, 1, until you have swapped every time the maximum, and finally your list is sorted. So that's what the code looks like. And if you then look at the complexity of these sorting algorithms, well, the first time, if you have 7 numbers, you do 7 comparisons to find the maximum. Then in the second iteration, you are going to do 6 comparisons to find the second biggest number. Then 5 comparisons, 4, 3, 2, 1, and so on. And so mathematically, this boils down to this series. So we go from from E to 0 to N, and then the first time you have N min 0, then plus N min 1, and so on. And you can deduce, you can rewrite that expression, and it means you have to do N times N min 1 by 2 steps. So that's for defining the number of steps with the function t. And if you look at the complexity, we say that the average runtime is n squared. Also, the worst case is also n squared, but the average runtime is also n squared. So that's not that good. We saw n squared, it can get into problems. If you have an input list of 1,000 elements, n squared means you're going to have you're going to do millions of instructions. If your input list has 1,000,000 elements, you're going to do 1,000,000 times 1,000,000 of instructions. So selection sort, it's terrible. And the only reason I show it to you is as a base example of an algorithm that's actually not efficient. So then we're going to Quicksort. As the name says, it's quick. It's a faster algorithm. It's also a more complex algorithm. So it's a recursive sorting algorithm. And how does it work? Well, basically, at each iteration, we select an element of the list, a random element. The only criteria is it appears in the list. And we split the list into 2 sections, namely all the elements that are higher than the pivots and all the elements that are lower than the pivots. And then after partitioning, we have 2 sublists. So if you have 10 elements to sort and you find maybe 3 elements, you have a list of 10 elements, and then maybe 3 of those elements are smaller than 5, 6 are larger than 5. Then you're going to take both sublists and sort them recursively. So you have reduced by partitioning. You have reduced your problem, and instead of solving n elements, you're now going to sort n divided by 2 lists, 2 sublists. And so finally, the recursion stops if there are only 1 or 0 elements in the list after partitioning. That's okay. So they do it complex, but I have an illustration here that will hopefully make it more clear. So here we have our input list. It's not sorted. And then we take as a pivot 4. And if you then look at the last line on the figure in the left, you see after partitioning 8, 9, 5, and 7, these are all the numbers bigger than 4. They're at the right side. And sorry, in 5 also. And on the left, you only have 3, 1, and 2. And so these small numbers are lower than 4, and 5, 8, 9, 5, and 7, those are bigger than 4. So that's partitioning. And then if you go to the next step, you see that instead of sorting one big array, it's divided now. You have only 2 sub-lists, and if you sort them and then join again the resulting lists, in the end, the entire list is sorted. So you first partition, then you have 3, 1, 2. Okay, you have to sort that. You find it's 1, 2, 3, and then you put it back in the results. 4, yeah, every number smaller than 4 is at the left of 4 and at the right of 4. So 4 is in its final position. And then 5, 8, 9, 5, 7, you still have to sort that. So again, we do that recursively. So that sublist, there we have 7. Again, we partition on 7. So 8 and 9 are put to the right. 5 is, it's repeated 2 times, and in the list you can have repetition. So they're both smaller than 7 and put on the left of 7. Then again, we recurse. We divide our problem and solve it. Divide and conquer. We have 5, 5. Okay, that's sorted already. Then we have 9, 8. There we have to sort, put 8 and 9 in the correct position. And finally, we have a solution. So it's a little bit complex, but that's a standard technique, this divide and conquer technique for creating more efficient algorithms. Here's the code. So I know if it's the first time you if it's the first time you see a recursive definition, a recursive function, you really have to, it really has to sink in. So it's not a lot of code, but it's difficult to grasp the first time you see it. And so here you have our quicksort. It takes an input list as argument. Now we can stop with recursion. So the list is sorted if there is only 0 or 1 element in the array left. So then we just return the array. And so by definition, every array containing only 1 element is sorted. And so that's the easy case. Then the next 6 lines are for partitioning. So partitioning is also not that difficult. You take, in this case, the pivot is the first element. You loop over all your elements in the array. And if any element in the array is smaller than the pivot, then you put it at the front of the list. So the first time an element you encounter is smaller than your pivot, you put it to the left of the pivot. You increase the position by 1. And so you don't sort, but you just throw everything that's smaller on one side and throw everything that's larger on the other side, using these swap operations. And then you have the recursive call. Well, it doesn't, question from Oberon, it doesn't matter for the final results, but how is decided what to do with the double value of 5 if the split is done on one of 2 5 values? Okay, so for the pivot, indeed, that's a good question. So if you have here 2 values that are the same, for the pivot comparison, you just put them, the condition actually here in the pseudocode is smaller or lesser than the pivot. So if you have 2 times 5, you just put 1 5 during partitioning on the left of the pivot, and that's okay. So that's how you do it. So it's not that it doesn't have to be smaller than a pivot, it can be smaller or equal, and that's fine. And then during the recursion, if you find that the other 5 is the largest element in the sublist, it will be sorted on the right. So, and here you have the recursive call. So here you know at current position, so that's the position of the pivot. And you know these are all elements smaller than the pivot. So if you sort that list and you sort all elements at the right of the pivot, and then you join them after calling that recursively, you know if you join these three arrays or merge them, you get the final array will be sorted. So that's how you solve it. And that was illustrated here. So what's the analysis of Quicksort? And this is where it gets interesting, because before with selection sort, we had an average runtime of n squared, and now the runtime is n times log n. So that's important, because n squared, if you have 1,000 elements, 1,000 times thousands is 1,000,000. Like with log 10 of 1,000, it's only 10. So here, if you have 1,000 elements as input, it's only 10,000 steps. So that's 100 times less steps you require. So very interesting. How do we come at that analysis? So we assume an assumption that the pivot element at each iteration splits the list roughly into 2 equal parts. And so instead of one big list we have to sort, we now have 2 lists which are half the size than the original array. And we do that at each iteration. The partition is linear in the size of the list. So swapping all elements lower and higher than the pivot at each iteration, that's a linear operation. And so if you look at the function t, well, the first time you're going to partition the whole list, so it will take n comparisons. And then the second term, now we have 2 lists, and each are roughly half of the original size. So we're going to do 2 times for 2 lists, n divided by 2 operations. So the n divided by 2, that's for partitioning the sublists. And then the next term, we're going to again recurse over that, and instead of 2 sublists, we now have 4 sublists, but each sublist is roughly 1/4 of the size of the original list. And we continue with 8 sublists, and each sublist is 1/8 of the original sublist, and so on. And so if you rewrite that, it's n times 1 plus 1 plus 1, but these are the number of terms you have are logarithmic. So we're not going to do a formal analysis here, but you can assume that if the list is roughly split in 2 equal parts at each recursion step, then we're going to have in total only a logarithmic number of terms. So the number of instruction you need, or the complexity, is n times log n. And that's the average case. So that's very nice for Quicksort. However, there's a caveat, and that is in the worst case, you can still have a complexity of n squared. So what happens in the worst case is that your pivot is always the maximum number. And then your lists are not going to be split into 2, and then you're going to have a result similar to selection sort. So in the worst case, Quicksort can still take a lot of time, but on the average case, it's quite fast. So that's an example of 2 sorting algorithms. So here's an overview of all the different sorting algorithms there exists. So how do you can ensure you choose a good pivot? So there are some strategies. And so one is just taking a random element. So it can be silly that a random element will be a good pivot, but if you have a large enough list and these numbers are distributed uniformly at random, just taking a random element, you won't have a neat partition into 2, but you will have a good partition. It won't be that your random element will be the maximum in the lists. So the chance of that happening at each iteration is small. So if you just take a random element, actually in almost all runs, for almost all input data sets, your actual runtime will be close to the average runtime of n log n. So that's one strategy. Another strategy is to take the median of 3 values. So then you take 3 random elements from the list, and then you take the medium, so the middle one. Yeah? So that's also a strategy to find a good pivots. So that pretty much concludes, I think, our presentation on algorithms. So here's an overview of other algorithms that exist for sorting, together with their time complexity and the best time complexity, the time complexity in the average case and in the worst case, and also the space complexity. So you can see here insertion, selection sort. It's a horrible algorithm actually, because it's n squared even in the best case, on average case, and so on. It has a very good space complexity, since you don't need to store additional data. All the data you need is just stored in the array. But yeah, it's a pretty terrible algorithm. And then you have Quicksort, which has an average a complexity of n log n, but in the worst case, it's still n squared. So if you want to avoid that worst case, there are other algorithms, such as merge sort, team sort, and heap sort, which are in the worst case also guaranteed to be n log n. So there are other algorithms. I think merge sort, heap sort, and team sort, they're pretty similar to Quicksort. They're all based on a divide and conquer approach and recursively processing your data. So that's an overview. So I have this last additional slide, but I'm not going to discuss it. Basically, the point I want to make here is that for algorithms which are quadratic or exponential, buying a faster computer doesn't really help. So even with a really fast computer, that maybe your new computer is maybe 10 times faster than your old computer, if you have an exponential problem, that won't help a lot. You will be able to process slightly bigger inputs, but not really get much progress there. Okay, so this concludes the first presentation on algorithms. The second presentation will be on data structures. I propose you can ask some questions now, and then we take a small break. So are there any further questions? Yeah, Charlotte?
Yes, thank you. I had a question on slide 17. So I didn't quite get the mathematical notation of the 3 kind of big O notation. So I was wondering why, for example, the constant C1 times C2 has to be greater than 0 in the average time case, for example. I didn't quite get the notations of those 3.
Okay. So the big O notation, so f1 is your t function. And the big O notation is to denote an upper bound. So that means that function is always bigger than your t function. So here you have a graphical representation in the middle in B, and then you have your O function, which is C times Gn, and then your original function. So like here, for example, we have a search problem, and we say on average, you have the function t. It's a constant time to run these different instruction, and on average, you will have to check n divided by 2 elements during a search before it stops and returns true. And in the worst case, you have to do n steps. So that's a constant times n. But for this upper bound, if you look at it exponentially, if you just have on instead of n divided by 2 or a constant plus n, then starting from some point, so for some input size bigger than n0, it will always be an upper bound for the original function. So that's why it has this notation. Yeah, we call this the sandwich lemma theorem. Yeah, I didn't. Within a computer science class, I would go into a little bit more detail than I have done now, but it's just to give the intuition. So it means here, if you drop the constant terms and only the leading terms, then if you have a really big input size, even by dropping those constant terms, it doesn't matter, because your big O function, if you multiply it by a constant, it will always be higher than the original t function. So is that a little bit more clear, Charlotte?
So if I get this right, the big O function is the worst case scenario always, and then the average case scenario is then the t function. So it's in the middle between the best and the worst case scenario.
Yeah, indeed.
And we don't have to get the mathematical notation in detail, like it's
No. That's not. We're not going to practice on that. It's just that you have the concept. So I think the essential slides is this one. You have this classification of algorithms based on the complexity. And ON for me, it just summarizes that in the worst case you need n steps, or n squared in the worst case you need n squared steps. And then you just have to remember like the worst case is important. Like here in search, it's important that if you search for a number, that in the worst case, if you search 11, it takes n steps. So that's ON. While in the average case, in average is if the element is in the list, sometimes it's at position 1, sometimes it's at position n, sometimes at n divided by 2. So on average, you do n divided by 2 steps. So we also say the average case is ON mathematically, theta n, or theta n divided by 2. You can also add, it's not completely correct, but that just means the number of steps it takes on average. So if you remember those concepts, then it's good. And if you understand those concepts, it's good. I don't think there will be any mathematical derivations on the exam or something. Good.
Thank you. Yes, thank you.
Okay, you're welcome. Any more questions? Okay, then I propose we take a small break and then continue with data structures.